Okay, so we're going to finish up the second half of section 4.4. So we've done that whole first page and got through the rational roots theorem, and then we're going to pick up right where we left off, where we are factoring completely given the fact that we know one factor of a polynomial. So here, number 6, part B, so we're going to factor this numerator, this cubic polynomial, completely knowing that x minus 4 is one of its factors. So to do that, we're just going to do the division of the polynomial divided by x minus 4. Since it's linear, we're in the form of x minus c, we can use our synthetic division strategy. So the c value of 4 goes in the box. We've got our coefficients of 1, -8, -61, and 308. Okay, so if you're watching the video now, you should pause it, and I want you to try and work through this one on your own, just to check your understanding of synthetic division and then continuing the factoring process. So now would be a good time to do that. So you can pause it, and then when you're done, you can hit play and skip to the end of my working through it and just check your work. All right, so we bring down our 1. 1 times 4 is 4. -8 and 4 add to -4. 4 times -4 is -16. Combine -61 and -16, and I get -77. And 77 times 4, or -77 times 4 is -308. And remember, we should expect a 0 remainder because we are sure that x minus 4 is already a factor of that. So far, after factoring out x minus 4, we get our remaining quadratic, which is x squared minus 4x minus 77. And then we want to continue factoring that. So I need something that multiplies to -77 and adds to -4. So 77's factors are 11 and 7. And if 11 is negative and 7 is positive, then those add to -4. So then we've got our whole final factored form of our original polynomial. So that's going to be x minus 4 times x minus 11 times x plus 7. Okay, so we're going to move on to the next page and look at how much information the factored form of a polynomial will actually give us about its graph. So in my opinion, this is the fun part because the factors tell us not only where the zeros are, but how the function is behaving at those zeros. So we'll get into that. Before we do, let's just review what we know about a function and its graph and how it relates to its total degree. So what are the possible degrees for this polynomial? So a couple things, I'm just going to jump to this. What can we eliminate? So what degrees can this polynomial not have? Well, it's clearly not linear, so it can't be of degree 1. It is not a parabola, and we know that parabolas are degree 2. It does not have the pattern of a cubic function, which is like that. So we know it can't be 3. In fact, because these ends are both pointing up, if you remember, the even function's end behavior always behaves the same way. So both ends either go up or both go down. And then odd functions like this cubic right here have opposite end behavior at each end. So really we know that this can't be 1 or 2 or any odd degree because of the fact that both ends are approaching the same direction. How many real zeros? So a real zero is how many times it actually touches the x-axis. So how many visible zeros can you see? So touching x-axis. So obviously if we look at it, we see it touching the x-axis 2 times. But we know that it's not degree 2 because it's not just a parabola. So because of that, the possible degrees would have to be no more than 4 or no less than 4. So the degrees for this, the degree of this would be at least 4. Okay, Now, multiplicity of a factor. So this is what's going to tell us how the graph is behaving at a specific zero. So the multiplicity of a factor is just the largest exponent. Oops. It's the largest exponent of each factor. Let me just give you a quick example here. Okay, so if I say, let's just use it. I've got a polynomial in factored form, x minus 1 to the 5th times x plus 3 times x minus 5 squared. Okay, so multiplicity, so the factor x minus 1 has a multiplicity of 5. So that's the degree of that factor. X plus 3 has a multiplicity of 1. Since there's nothing there, we know it's 1. And x minus 5 has a multiplicity of 2. So that's what multiplicity is. If a factor has an even multiplicity, that's going to result in what is technically called a point of tangency. So we'll write that down and then I'll give you my layman's term for that, a point of tangency. So a point of tangency is a point where a function is touching a specific point at exactly one spot. So in other words, what I call it is it bounces off the x-axis. Bounces. So if a factor, so this x minus 5, this would mean I have a 0 at positive 5, and at that 0, the graph is bouncing off of it. So you may start remembering some of this from Math 3. We did look at this from Math 3, and we're just kind of taking it a little bit further. So an odd multiplicity results in a point of inflection. Inflection, and the term you'll hear me use, and you heard me last year, is that it squiggles through the x-axis at that point. Squiggle. Okay, obviously those aren't like formal terms, but maybe it'll help you remember it. So let's look at what I mean here. So if we've got the graph right here of x times x plus 1 times x minus 2 squared. I just want to stop and notice the total degree. I see both ends going up. That means this must have a total degree of an even value. And then the total degree is actually always going to be the sum of the multiplicities of each of the factors. So since this factor right here of x has degree 1, x plus 1 also has degree 1, and x minus 2 is, or multiplicity 1, multiplicity 1, multiplicity 2. This means total degree is 4. And then let's look at what's happening. So at my 0, so to find the zeros, you just set the whole thing equal to 0, set each factor equal to 0. And we've got our 3 zeros. So let's look what's happening on the graph at 0. Well, since 0 had multiplicity 1, that means it's going to behave, think about a line, because a line is a first degree polynomial. When a line crosses the x-axis, it just cuts through it just smoothly and straight through it. Then look at x plus 1. So at the 0 of negative 1, because we have x plus 1, that factor, and 0 being multiplicity 1, again, it's going to cut straight through the graph. So it's not bouncing, it's not squiggling, it's just cutting straight through. And then we look at the factor x minus 2, which has multiplicity 2 at the 0 of 2. That means it's going to bounce off of the x-axis. That's a point of tangency because it's touching the x-axis at one point and then without cutting through it. So that's how you break down the factored form of a polynomial, and you can sketch what the graph is actually doing at those zeros based on what that multiplicity is. So here's another one. So this one, right off the bat, before I even get into the zeros, if we look at this, we know for sure it has to have an odd degree. And again, the total degree of a function is the total sum of the multiplicities. So I have multiplicity 1, multiplicity 1, multiplicity 3. So this function is a 5th degree, or degree 5. And then let's look at what's happening at each 0. So if I want to find the zeros, you set it equal to 0, set each factor equal to 0. When the graph is reaching its 0 of 0, it's linear, or multiplicity 1, and it's going to cut straight through the graph. Same thing at -1 by setting this factor equal to 0. It's multiplicity 1, it's cutting straight through the graph. And then x minus 2 cubed, so this is giving me a 0 of +2, but that multiplicity of 3 means it's going to squiggle through, so that's why it's kind of bending. That point of inflection is kind of like a bend, just like we know that parent function of x cubed does, so it kind of bends through that x-axis right there. So let's see if we are looking at a graph now, and then based on this, we're gonna try and form a possible equation for this. So what can we tell about the degree of this function? The first thing I noticed here is that I've got two ends doing the same thing, so it's at least even. It cannot be 2, so that makes sense because it's not a parabola. And if you just look at it, it's got 3 real zeros. So that would mean it has to be more than degree 2. But it can't be a 3rd degree polynomial because it's not odd. So that leaves us with 4 being the absolute minimum at first glance. So at least degree 4, and then we'll kind of break it down. So if I know that I've got 3 real zeros and I can see what the graph is doing at each of those, we can actually build a possible equation for this. So think about what this 0 at -4, if I know that -4 is a 0, then we should be able to work backwards from that to build my factor. So if x equals -4 is a 0, then what would the factor be? So again, you would just add the 4 over, you would get x plus 4 equals 0, and now I'm looking at one of my factors. So x plus 4 is a factor, but because of how the graph is behaving there, I can also figure out what the multiplicity, or at least the smallest possible multiplicity is. So since I have a point of tangency, or a bouncing off of the graph, that means that this factor has to be an even multiplicity, so we'll say at least 2. Then I look at my next 0, which is -1, which means my factor will be x plus 1 for that. And then what is the graph doing there? It's cutting straight through. It's not bouncing, it's not bending. That's going to be that 1st degree pattern of a 0. So that would just be to the 1st degree, or you could just not write anything after it. Then I have the 0 of -3, which would produce a factor of x. I'm sorry, a 0 at +3, which would give us a factor at x minus 3. I'm looking for my whiteout so I can fix that. So we've got x minus 3, and then here we see it bending through. So a bending through means it's odd, but at least greater than 1. So this would have to be at least a 3rd degree, or a multiplicity of 3 for the factor x minus 3. So here's a possible factored form of a graph. This isn't going to be perfect because I'm sure there's some a value out here or stretch factor involved to get this exact graph. But this is what our factors would be, and these are what their possible multiplicities could be. So now the total degree, if we were saying it before, it could be at least 4. But now we actually see that since this 0 had multiplicity of at least 2, and this one has to be at least 3, then that means we have the smallest degree would actually have to be at least 6. So this is degree 6 or higher. And or higher meaning this could technically be like over here at 3, that could be a multiplicity of 5. We just don't know for sure, but it would have to be at least 3. Okay, so let's flip it over and practice this a couple times. I'm going to walk through 9 with you and then have you pause the video and try 10 on your own. But we're kind of working backwards now. If I'm given the equation in factored form of a polynomial based on its zeros in the multiplicity of each one, we can actually sketch a graph of this. Before you jump in and start plotting the zeros, because we're going to need to put points at each zero because I know that's where the graph is going to touch the x-axis. We need to think about the total degree first, just so we know where the graph will start and end. So the total degree. So again, add up all those multiplicities. We've got 2, 3, 4, 5, 6, 7, 8. So this total degree is 8, and that matters to us because I need to know where my graph starts and ends. So it's even, so that means they're both going to point up or down. You just have to figure out, do they both point up or do they both point down? Since my leading coefficient here is just +1, that means my graph is going to start and end both pointing up. So I know that that's how it's going to start and end, and then how it behaves in between, I'm going to use each of these zeros. So if we list out our zeros, we've got a 0 at 0. That's what that x squared is going to give us. And that's multiplicity 2. So I'll put the multiplicities down here as well. Multiplicity 2. -6, multiplicity 2. +2 with a multiplicity of 1. And +5 with a multiplicity of 3. So again, all the multiplicities add up to 8. And now we'll start by just plotting our points or where our zeros are. So I've got 1 at 0, -6. So you can scale this out just by hand. 2, 3, 4, 5. Okay. I'm going to have to move my little arrow over a little bit. Starting up there. Okay. And then I've got a 0 at -6, 0, 2, 3, 4, and 5. Okay. All right. From there, you can start sketching. So left to right, starting at -6. This polynomial is degree 2 or has multiplicity 2 for the 0 of -6. So I know that it's going to be bouncing off at that point. So I can go down and come right back up. And then before I continue any further, I'm going to go look at my 0, which is also multiplicity 2. So basically my function needs to go up and then bounce back off of 0. So in between, it doesn't really matter how high it's going. We're just sketching a possible graph. Okay, and then I'm going to stop. And my next 0 at 2 is multiplicity 1. So that means I need to go back up and just slice through that 0. So it's just cutting straight through the x-axis at 2. And then my last 0 at 5 is degree or multiplicity 3. So it's going to bend through it. So these are a little bit harder to graph. But you can see my attempt at making this bend through at 5. So all of your zeros should match, or the behavior at all of your zeros should match the multiplicity. So what I want you guys to do now is pause and try number 10. Actually, before you pause and try number 10, I want to point out the fact that it does have a negative leading coefficient. This -2, by the way, is not a 0. So this -2 is just the leading coefficient. -2 is a 0, but that's coming from this factor. This -2 is tells us the fact that there's a vertical stretch by 2, and the negative means it's reflected over the x-axis. So when you're looking at total degree of this function and where it will start and end based on that total degree, you need to keep that negative in mind because it is going to reflect it over the x-axis. So pause and try it on your own, and then I'm going to walk through it, and then you can resume the video and check your work. Okay, the first thing I want to do is figure out the total degree here. So my total multiplicity is 1, 2, 3, 4, 5, 6, 7. So this is a total degree of 7, which means my end behavior is going to be opposite. So it's going to start down here, end up here, or the opposite of that. So you need to determine where it is going to start and end. My advice is just think about what you know about the parent graph of x cubed. So x cubed, the parent graph x cubed, x to the 5th, x to the 7th, they all behave in this same way in terms of end behavior. So it starts in the negatives and ends in the positives. So this leading coefficient of -2 means our graph is actually going to start up here and end in the negatives. So that means it's going to be starting up here and ending down in the negatives. So that's how we know where it's going to start and end. Next, I'm going to put my zeros and their multiplicity. So I've got a 0 at -5. So I'll list those out down here. -5, 1, -2, and 4. So -5, +1, -2, +4. So multiplicity of -5 is 1. So that means it's going to be just cutting straight through the x-axis at that point. So I start my function here, I'm just slicing straight through. My next 0 is at -2. So that'd probably be right here. And the multiplicity is also 1. So at -2, I'm going to go down, and then at -2, slice back through it. So not bending, not bouncing, just cutting straight through. My next 0 is at 1. And at 1, right here, the factor x minus 1 has multiplicity 3. So that means my function is going to turn, come back down, and bend through the axis at 1. So there's my little bendy through, the point of inflection right there. And then my last 0 at 4 has multiplicity 2. So that means at 4, my function before it gets to 4 needs to turn back around, and then it's going to bounce off at 4. And then end in the negatives, just like that. So that's how you would build that one. When you're sketching these graphs, I'm checking for, are your zeros in the right spot? So make sure you label your zeros on the x-axis. I'm checking to see that the function is behaving in the correct way based on the multiplicities, and also that it's starting and ending in the right quadrants. Okay, so that's it for the second half of 4.4.